Okay, hello. So now we're going to go through some probability examples, and this will be the first part. We'll do this in two parts. So the first part is going to be mainly the material from Chapter 5, which is basic probability, and then which is number 1 through 14 on these examples here. And then the second part is the rest of it, which is Chapter 6 stuff, random variables. So there's going to be two variables, this is two videos. And this is the first of two. Of course, there's a worksheet to do along with this that is very similar to this. So if you watch this, you ought to be able to, to do the worksheet along with it. And this is a nice review of probability. Obviously, I'm not going to cover just every little nook and cranny of probability. And there's a lot of different types of problems that can occur, a lot of different curveballs that can be thrown. And the way to get good at it is, I think, understanding the basic stuff like this and then doing a lot of practice. So I encourage you to do that in your textbook, in your Barron's book, or in the Sapling or in the AP classroom. There's a lot of opportunities to get to get practice in regards to probability. But anyway, so let's so the Chapter 5 problems, the basic probability. There's the types of problems you have to understand. Basically, you have to understand how to do a Venn diagram problem, which is going to be what we're fixing to do here in the first, context 1, how to do a tree diagram problem, and how to do a two-way table problem. Those are the main three types of problems. Then we also have the use of formulas and independence. So our formulas on our formula sheet, which we'll be making reference to, there they are on the first page. So there's our generalized addition rule, and then the probability of A or B is equal to the probability of A plus the probability of B minus A and B. And then the conditional probability, the probability A given B, is equal to the probability of A and B over the probability of B. So those are in your formula sheet. And then your independence formulas, which we're going to talk about when we get there, you just have to memorize those. You have to understand those. So anyway, let's look at these problems here. So the first context is 20% of seniors at a high school take AP Stats, 12% of the seniors take AP Calculus, and 9% of the seniors take AP Stats and AP Calculus. If you randomly select a student at the school, find the probability that they, and so whenever you're probability one thing, probability the other, probability of both, there's a good chance a Venn diagram is going to come into play, and so we'll make us a nice little Venn diagram. And so this circle represents all, and so our whole population here is all the seniors. So the rectangle represents all the seniors at this high school. And so this represents stats. I'll put S for stats. And so it says 20%, so I'll put 0.2, like that. So that 20%, so if we're doing this to scale, 20% of this rectangle will be taken up by that circle. And then we've got this other group here that is calculus, and so that is 12%, 0.12. And there is some overlap. It says 9% or both, and so that's this football-shaped region there. If there was no overlap, then the two events would be disjoint. There would be no overlap, or what we call mutually exclusive. In other words, if there was no overlap, there was nobody that's taken stats and calculus, and so mutually exclusive means if I told you someone takes stats, they cannot take calculus. But that's not the case here. We do have some overlap. So anyway, now to fill out the rest of this tree diagram, or Venn diagram, the way I do it is I say that minus that, 0.2 minus the football-shaped region, that would be 0.11. And that represents people that take stats but not calculus, this crescent-shaped region there. And then if I go that minus that, that's 0.03. That means it's in the calculus circle but not in the stat circle. It's this region here. And so, so you notice the two parts add up to the whole for each of the circles. And then lastly, the outside, the whole rectangle has to add up to 1. So when you add up these four regions, that, and that, they have to add up to 1. And so in this case, when you add that plus that plus that, it adds up to 0.23. So 1 minus that's 0.77. And so there's a Venn diagram, and they could ask you a number of questions from here on out. And I want to use the formulas as well. But so stats or AP Calculus, now that means stats or AP Calculus or both. So in other words, you would add up these three numbers here, which would add up to 0.23. It's the area on the inside of this circle. But or means add. If you're using your formulas on your formula sheet, that is what we call the generalized addition rule right there. And so it'd be probability of one plus the probability of the other minus probability of both. So in this case, the little formula would be, so the probability of stats or calculus is the probability of stats plus the probability of calculus minus the probability of stats and calculus. And so that in this case would be 0.2 plus 0.12 minus 0.09, and that's equal to 0.23. But showing the Venn diagram would be considered showing your work, but that's showing the work with the formula. Right? Take calc, what's the probability they're going to take calculus given they take stats? All right, so calc given stats, that is the other main formula we have, the conditional formula. So the probability of one given the other is the probability of both over the probability of the second one of the given. And so that is going to be equal to the probability of calculus and stats over the probability of the second one. And so that is going to be 0.09, that is the probability of both, over the probability of stats, and that's 0.2. And so that, as it turns out, is equal to 0.45. So that's 0.45. That's our conditional thing. And so, in other words, this is the probability. If I told you that a person takes stats, what's the probability they're going to be taking calculus? And it's 45%. And you may notice at this point, these events are not independent. Because in general, the probability that someone takes calculus is 12%. But if I told you that they took stats, that probability goes up to 45%. So the occurrence of one has changed the probability of the other one. And so they're distinctly not independent. But anyway, let's not get too far ahead of ourselves. What's the probability that they take calculus but not stats? In other words, it's in the calculus circle but not in the stats circle, and that's 0.03. Or if you were showing your work without doing the Venn diagram, you could just say, what's calculus but not stats? Take all the calculus kids, 12%, and subtract off the 9% that are taking stats, and so it's 0.03. So that would be that. Okay, and then show whether or not they're independent. Now, there's two independence formulas you have to be aware of. If they're independent, the probability of one, the probability of stats, times the probability of the other is equal to the probability of both stats and calculus. And calculus. So that is sort of the most popular formula for independence. And so in this case, this would be, if that's true, 0.2 times 0.12, it would be equal to the probability of both, which is 0.09. And as it turns out, that times that, these are not equal, so that would be 0.2 times 0.12 is 0.024. That is not equal to 0.09. Therefore, they're not independent. They are not independent. So that's one way to show it. The other way to show it, the other formula for, so that's one formula for independence. The other, if they're independent, the probability of one given the other, calculus given stats, is just going to equal to the probability of calculus. And so in this case, calculus given stats is 0.45. That is not equal to the probability of calculus 0.12, so therefore they're not independent. So either you have to be able to use both of those formulas, to be honest. All right, and then lastly, in regards to this context, let's say there's 400 seniors at the school. If you randomly select 3 of them, what's the probability they all take AP Stats? This is a multiple event. And when you encounter a multiple event, 3 things happen. You multiply them, okay? And the only way you can multiply them is if the events are independent, which they're not here, or if you take into account their conditional nature. And the conditional nature means this. All right, we got 400 seniors. What's the probability that that first one takes stats? Well, okay, well, and you would say to yourself, all right, well, I know that 20% of the students take stats, and so you would say, 0.2 times 400, and so therefore it's 80. So 80, so the probability that that first senior I select that takes stats is 80 over 400, okay? Now, given the first one takes stats, the probability the second one takes stats is now 79 out of 399, because I've taken one of them out. Okay, so there's only 399 of them left, and only 79 take stats. Given that the first 2 you've sampled take stats, the probability the third one takes stats is now 78 out of 398, because we've taken 2 people out. And so you multiply the probability of multiple events. You multiply these things, and I've taken into account their conditional nature, so I can multiply them. And when you do that, well, so that's showing your work, and so let me see what that is. And so that is going to be 80 times 79 times 78 is equal to, and divided by 400, divided by 399, divided by 398. And so that, as it turns out, is approximately equal to 0.0077606. So I think I did that right. Okay, so there you go. So in other words, it's pretty unlikely to happen. So there you go. All right, so that's the first major type of problem, is Venn diagram problems and problems dealing with our formulas, with our addition rule and with our conditional and with independence there. Okay, so now let's look at our second scenario. All right, so this one says this: 40% of people in the village got a flu shot. If they got a flu shot, the probability they got sick with the flu is 0.06. If they did not get a flu shot, the probability they got sick with the flu is 0.24. If you randomly select someone from the city, find the probability that. Okay, what you need to recognize here. Now, you can't really make a Venn diagram with this information because we don't have the probability of one thing, probability of the other, probability of both. All right, you need to recognize these are conditional statements. And when you're given conditional statements, then a tree diagram is probably the way to go. Conditional means the probability of one thing given another thing. And this is another way of wording. Another way of wording this: given they got the flu shot, the probability they get the flu is 0.06. Okay, and so we're going to make a tree diagram out of this problem. There can be a lot of sort of trial and error in regards to probability. Probably try one way, and if it doesn't work, you try another way, so let's look at this here. So it says 40% got a flu shot. So I'll do this. So the first event, I'll put S for shot. So 40% got the shot. That means 60% did not get the shot. So that we call that shot complement. So given they got the shot, the probability they got the flu, I'll put F for flu, is 6%. So I'll go 0.06. What that means is that the probability they did not get the flu, which would be flu complement, would be 0.94. Each of these pairs of branches have to add up to 1. Given they did not get the flu shot, the probability that they got the flu is 24%. So that's 0.24. And so probably they did not get the flu would be 0.76. Okay, so there's our tree. And so we've got to find the probability of each of these branches, and you multiply the branches. If you were to randomly select one of these people, what is the probability they got the flu shot and they got the flu? That means multiply. That times that. So that's going to be 0.4 times 0.06, and that in fact is equal to 0.024. What's the probability that someone got the flu shot and they did not get the flu? Okay, and that would be 0.4 times 0.94, so that's 0.4 times 0.94. And so that, in fact, is equal to 0.376. Okay, then what's the probability someone did not get the flu shot and they got the flu? And so that's 0.6 times 0.24, and that, as it turns out, is 0.144. And then lastly, what's the probability they did not get the flu shot and they did not get the flu? And that is 0.6 times 0.76. And so that would be 0.456. Now, first of all, I think what you notice about this scenario is the fact that these variables are certainly not independent. And you wouldn't think they would be. I mean, the whole point of a flu shot is that it makes you less likely to get the flu. And so, if they get the flu shot, there's going to be a 94% chance they don't get the flu. But if they don't get the flu shot, there's a 76% chance they don't get the flu. So anyway, so let's answer the questions that we get. So if you randomly select someone from the city, what's the probability? So this would be, what's the probability they did not get the flu shot? So they did not get the flu shot and they got the flu. So they did not get the shot and they got the flu. Well, that's this scenario. That's this one here. So that would be 0.144. And drawing the tree diagram would be showing your work. You could just say 0.6 times 0.24. So, and just write that, and that would be showing your work. All right, what's the probability they got the flu? All right, there's two events where they got the flu. They got the flu here, that group got the flu, and then this group here got the flu. Those two. And so we add up their probabilities. So that is going to be 0.024 plus 0.144, and that in fact is equal to 0.168. right like that. All right. And then these are what is known as Bayes' theorem problems, which we don't have to cover the formula of Bayes' theorems, but it just is a reversal of conditional. Okay, what's the probability they did not get the flu shot given they got the flu? In other words, okay, given you see someone that has the flu, what's the probability that they did not get a flu shot? All right, so what's the probability that they did not get the flu shot? They did not get the flu shot given they got the flu. Well, that goes back to our old friend, the conditional formula here. The conditional formula, A given B is A and B over the probability of B. So this is just going to be equal to the probability of not getting the flu shot and flu over the probability of flu. And so that, as it turns out, that is this, not getting the flu shot, that'd be 0.114, so that'd be 0.144 over the probability of flu is what we just found there, 0.168. And that, as it turns out, is 0.8571. So if someone in this village has the flu, there's a pretty darn good chance they did not get the flu shot. Okay. And then lastly, in regards to this scenario, in a similar sort of problem, what's the probability they got the flu shot given they did not get the flu? So the probability they got the shot given they did not get the flu. Okay. Well, our formula again, that's going to be the probability of that and that over the probability of the second one. Okay, and so that and that, so this would be shot and not flu, so that would be 0.376. And then over the probability of not having the flu, and that's these two groups. That is that and that. And so when you add those two together, you would, well, it would be 0.376 plus 0.456, and that, as it turns out, is equal to 0.45194. So there you go. And so that's how you do tree diagram problems. That's about everything that can happen to you on a tree diagram problem. So there you go. All right, and so then the last scenario I want to chat about today is in regards to 2A table problems. A lot of these 2A table problems I think are pretty intuitive. In other words, I think you can, many times you can kind of figure them out even without having AP stats. And so in this particular scenario, it says the dictator of a small island country decided to give each person of his island a gift. They each got to choose whether they wanted to receive a canoe, a bicycle, or a sword. He notes how many of each gift people got and whether they lived in the city, which is located in the middle of the island, or lived along the shore. So here they are. Here are the people that live in the city. They had 46 canoes and 589 bicycles, 112 swords. And then the shore people, they got 62 canoes, 22 bicycles, and 44 with the sword. Okay, and so then it asks, if you were to randomly select one of the people from the island, find the probability of that. So whenever you're given one of these 2A table problems, what I encourage you to do is to come up with your marginal distributions. And I have figured this out beforehand, if I can find it. Yeah, here we go. And so come up with your marginal distributions. In other words, add these up. There's a total of 108 that ordered the bicycle. There's a total of 611 that wanted the bicycle. 108 wanted the canoe. 611 wanted the bicycle, and 156 that wanted the sword. So when you add those up, the total number of people on this island that this guy's a dictator of is 875. All right, the total number of city dwellers, 46 plus 589 plus 112, that's 747. And then the total number of shore people is 128 when you add up those three numbers there. And so there's our marginal distribution. Now, of course, there can be different problems asked about this. They could ask you to graph this. And so, of course, what sort of graph would you make? That's right. You'd make a side-by-side bar graph, all right, which you would need to come up with the percents here. In other words, the relative distributions. And anyway, but we're not going to talk about that. And of course, we could do a chi-squared test, but y'all aren't learning that this year because they've cut that out of the curriculum for this year. But at some point, I'll post a video so you can know that. But that's not going to be in the exam this year, so you don't got to worry about it now. So let's answer the question that's being asked. And so if you were to randomly choose one of the people from the island, find the probability they are a city dweller or want a canoe. So you could just add up the city dwellers and then put the non-city dwellers at a canoe. Or, the word or means add. And so what you could do is you could say, well, that means city dweller. Okay, if you were to randomly select one of these people, what's the probability they're a city dweller? Well, that is 747 out of the total of 875. And then or means add, plus how many want a canoe? Well, the total canoe people is 108, so it'd be plus 108 over 875. But the problem is, whenever you add probabilities, you have to subtract off any overlap. You counted these city dwellers that got a canoe twice, so you have to subtract them off once. And of course, that's the generalized addition rule that's on your formula sheet. The probability of one thing or another is probability of one thing plus the probability of other minus the probability of both. And that, in fact, is equal to 809 over 875. And so that's approximately equal to 0.9246. So, and once again, on these problems, make sure you show the fraction that if you showed the fraction, that'd be considered showing your work. You don't have to put the decimal. Are a city dweller given they want a bicycle? All right, given they want a bicycle. When these conditional problems, you only look at what you're given. Okay, that's all there is to. So all we're given in this problem is the 611 that ordered a bicycle. So if you randomly select one of these 611 people, what's the probability they're from the city? Well, that would be 589 out of 611. So the city dwellers tended to like getting a bicycle in this scenario. So that's about 0.96399. So that's the answer to 11. All right. What's the probability they wanted a canoe given they are from the shore? All right, given they're from the shore. In other words, you can only look at what you're given. I can only look at the shore people, which is this row. These 128 people. If you randomly select one of these 128 people, what's the probability they want a canoe? Well, there's 62 that want a canoe out of 128, and so that is approximately equal to 0.4844, like that. All right, show whether or not being from the city and wanting a sort are independent. So if they're independent, the probability of one times the probability of the other is going to be equal to the probability of both. Okay? And so what's the probability they're from the city? Well, the probability they're from the city is 747 over 875 times the probability that they want a sword. Well, the sword, that'd be 156 out of 875. Is that equal to the probability of both, which is sword and city? Sword and city is 112 out of 875. Okay? And as it turns out, the left side there is 0.1522, and the right side, that is 0.128. They are not equal, therefore they are not independent. They are not independent. Okay, so you could have also done the conditional like we did before, but anyway. Okay, and then lastly, as far as what we're covering in this video, if you randomly select 3 of the people from the island, what's the probability they all want a bicycle? And so once again, multiple events you multiply. So what's the probability the first one wants a bicycle? Well, that's going to be 611 out of 875. Okay. Then given the first one wants a bike, what's the probability the second one wants a bike? Now 610 over 874. And then lastly, what's the probability the third one wants a bike? Given the first 2 wants a bike, well, there's only 609 people left that want a bike, and only 873 in general, and that, as it turns out, is equal to 0.33998, 0.33998. And so, okay, that is it for the first part of probability, which is mainly the Chapter 5 stuff. And so do a good job with that part of the worksheet, and we will have another video in regards to random variables, which Context 4 is starting with.